tell you a bit about the ideas that lead up to black holes, some of the paradoxes they introduce in physics, and some of the ideas we have for fixing those paradoxes and understanding even more things about space and time at a microscopic level. So, first of all, I will. Okay, thank you. First of all, a little bit about the talk and what you can expect to find in it. There are two big ideas. There's no math. Although, if you do like math, ask me because math is lurking just behind this, but don't worry, in case you have allergies or just don't like it, it won't be here. So that's what you might expect. Let me begin by saying a little bit about science in general, the goals of science and physics in particular, that will sort of inform the attempts that are being made to discuss black holes and how to merge them with some of our ideas about what happens in physics at a subatomic level. So the main goal for its whole history of science has been to find something puzzling, some phenomena that we observe and that we don't really know how to explain, and to relate it to something that's happening at a more basic level. Maybe substructures of whatever object we're trying to explain. Maybe substructures can explain the properties of things. For example, heat. People have been noticing heat forever, and in the 19th century, science was able to explain heat in terms of microscopic motion. So atoms and molecules within some object are moving very vigorously when something is hot, and this is the true explanation of temperature. So this is a success of science to be able to take something that we observe at a large scale and relate it down to something more basic and be able to explain one phenomenon in terms of other things we understand better. Or another example would be, for a long time people talked about matter in terms of solidity, the solidity of matter. You know, if I bump this podium, I can feel it resisting me, or if I clap my hands, they bounce back from each other. It turns out this also can be reduced to something more basic. It turns out that if you would look at my hands, they're made of such a sparse number of atoms that they could, in principle, when I clap them, pass one right through the other. But what's making them bounce back is that on the outside of the atoms in my hand are electrons. Electrons all have a negative charge, and like charges repel each other. So when I bring my hands very close together, what actually makes them not pass one through the other is that there's a repulsion of like charges, and that's really what the solidity of matter is. It's not that there's some basic property called solidity that's inherent to matter. It's explainable in terms of something more basic. So this is what we would like to do in the case of forces, for example, like especially the force of gravity. This is the first indirect force that people noticed and began to try to explain. By indirect force, I mean that it's not the case that when you see something behaving under the influence of gravity, you don't see that object being actually physically touched and pulled. There's nothing from the sun that holds the planets in place in orbit around them. There's no rope going from the Earth to the moon that's holding the moon in orbit around the Earth. So it's more difficult to understand what actually gravity is. And even Newton, who is the first person to explain things about gravity, he was the first person to realize that it's really all the same force, the force that keeps the planets in orbit around the sun, that keeps the moon in orbit around the Earth, and that makes an apple fall off of a tree. That's all the same force at work. Even he was not able to explain what's going on at a more basic level. What really is it that's, say, when you shoot a cannon, what's making the cannon be pulled toward the Earth? So this is just an illustration. Newton's cannon is an illustration of how different motions that we see are all due to gravity. What Newton said was that if you had a mountain on the North Pole and a cannon was installed on that mountain, various things could happen, but they would all be due to gravity acting in different ways based on the motion of the cannonball. If you shot the cannon not very hard, it would fall down to the Earth. If you shot a little harder, it might go into orbit around the Earth, just as the moon is in orbit around the Earth. Or if you shot it even harder, it might be able eventually to escape the Earth's gravity and go off somewhere else the way a rocket launch does. So that was his achievement, that he realized that all of these different motions were due to the force of gravity, and mathematically he explained them in a unified way, but he didn't say what it was that was actually physically tugging that cannonball toward the Earth. This had to wait for Einstein, who said that what gravity is it's really just geometry at work. He said, let's say there's this tree with apples on it, and the apples can fall from the tree under the influence of the Earth's gravity. What's happening is that space is not something inert that the apples just fall through without interacting with. Actually, the way gravity works is that the geometry of space is changed by the presence of the Earth, and the apples are interacting with space as they fall. Space is something dynamic. And it actually has a changed shape because of the Earth being there that influences the motion of the apples. So, slightly more specifically, could say that the presence of matter and energy, like the presence of the Earth, causes a bending of space. And so an object like the moon that's in orbit around the Earth is just responding to that curvature of space. It's moving in the way that makes most sense for it to move, given the fact that space has become curved by the Earth being there. The central equation of general relativity is called Einstein's equation, and what it really says is that if you have matter or energy, if you have the objects in this room, this podium, the table, the chairs, the people in the room, all of us are slightly bending the space of this room and slightly changing the way any particle that comes into the room, a particle of dust, we're changing the way it might move because we're curving space, and that particle has to alter its motion in response. So Einstein's equation says that matter equals curvature. Matter will directly cause curvature of space-time. Or if you want what gravity is, it's just equal to geometry, the geometry of space-time. So this was a true reduction. This was a true being able to say that gravity is a phenomenon we observe, but it could be explained in terms of something more basic, space-time curvature. So if the universe didn't have matter in it, on the other hand, you can also say that cannonball, the cannon that Newton shot from off the top of the mountain in his thought experiment, that would not have followed a curved path at all. It wouldn't have fallen down toward the Earth, or if you shot it slightly harder, it wouldn't have gone into orbit around the Earth. If the Earth weren't there, the cannonball would go in a straight line because space-time would be flat, and so there's no curvature that it has to account for in its motion. But if there is some matter, any matter, no matter what, there, space-time will become curved, and all that cannonball is trying to do when it follows a curved path is it's trying to take the shortest path between 2 points. Everything always wants to travel in the most efficient way. But when you have a curved space, you actually have to throw out the concept of a straight line. You can no longer say, okay, a straight line is going to be the shortest line between 2 paths, 2 points that you want to travel along a path between. What does it really mean if you had, say, an ant that's living on the surface of a beach ball or some other curved object? You can't really say what it would mean for the ant to go in a straight line from this point on the beach ball to this other point. You have to throw out that concept altogether and say, all right, if you have a curved space, talking about straight lines no longer makes sense. You just have to talk about the shortest path between 2 points and what gravity will do, what the presence of matter will do. It will curve space-time, and it will make it be that these particles that are moving under the influence of gravity, the moon or whatever it might, the apple, whatever it is, it's still just trying to take the shortest path between 2 points, but that's going to be a curved path because space is curved. So let's look in a little more detail about what Einstein's equation does, this equation that tells us that all matter is really doing is it's curving space, and that's what gravity is. So the equation works like this. It's like a box, and you put into the box some information about what matter is present in this room, and the equation cranks some gears, and as output it gives you a description of the curvature of space. And the way it does that is it tells you if you would travel around this room with a measuring tape, because the space of the room is curved from the presence of matter, you would actually find that the measuring tape is warped, and it warps differently depending on where you are and depending on what matter has caused what kind of curvature in the room. And Einstein's equation would tell you, if you solved it, it would tell you exactly how that warping action of the measuring tape would happen based on the distribution of matter and energy in the room. So you can ask, how would this work in a really extreme situation? The most extreme situation we can imagine, a black hole. What if a black hole were in this room? How would our measuring tape behave if we walked around from place to place? So let's back up. What is a black hole? And it might seem it's something very modern, a new invention of general relativity, something Einstein came up with, but that's actually not the case. Surprisingly enough, people have known since 1783 that it was theoretically possible to have a black hole using Newtonian gravity, the gravity that Newton was able to work out. This is a letter from a geologist named John Mitchell to Henry Cavendish, who was a fellow of the Royal Society. And in the letter, John Mitchell suggested the possibility that there could be something that he called a dark star, which is essentially what we would now call a black hole. So how did he work it out? What was his reasoning, and what kind of an object was he envisioning as a dark star? So he used Newton's theory of gravity, and he actually used that idea of Newton's cannon that I was just mentioning, where you had a cannon on the North Pole, the cannon was sitting up on top of a mountain, and you shoot a cannonball, and the way the cannonball moves will depend on how fast, how much power you shot it from the cannon. It might fall to the ground, it might go in orbit around the Earth if you gave it a little bit more energy, or if you gave it even still more energy, when it left the muzzle of the cannon, it might fly off somewhere else and escape the Earth's gravity. So we have a quantity to make this notion precise. The quantity is called the escape velocity of a particular object. So if you were on the Earth, or if you were on the Moon, or Jupiter, or wherever, there would be a particular speed threshold that's called the escape velocity, and it would be how fast do you have to make something move in order for it to escape the gravity of wherever you are. On Earth, the escape velocity is 11.2 kilometers per second, so when we launch a rocket into space, we have to make sure that it leaves the surface of the Earth at 11.2 kilometers per second, very, very fast, and if you do that, it will escape the Earth's gravitational field. So all of this was known back in the times of Newton. He figured out the concept of escape velocity, and in the 1780s, people had this concept. So here was what John Mitchell thought. He thought, what if you had some kind of an object whose escape velocity was so high that it was equal to the speed of light? If that would happen, let's say this object tried to emit some light, maybe it was a star, or maybe it was a planet with a person standing holding a flashlight. If the escape velocity were equal to the speed of light, then even light will not be able to escape from this, and you would have an object that was completely dark because it can't emit any light at all. All light that it tried to emit would be pulled right back to it, just the way a cannonball that was shot not hard enough would fall right back to the Earth and would never escape. So people contemplated this idea, and to get more deeply into it, you'd have to think about, on a particular, some particular planet, what would determine the escape velocity? It's determined by two things, it turns out. It turns out that you have to know how heavy is this planet that you're trying to escape from, and also how big is it. Those are the two factors you need to consider. And if you have a planet that's very massive, like Jupiter, let's say, its extreme mass will be contributing to having a high escape velocity. It's saying Jupiter is so massive that its gravity is quite powerful, and you'll have to shoot off a rocket at a very high speed from Jupiter in order for it to escape. But also, Jupiter is not a very dense planet. It's big and fluffy. And the fact that it has a large radius is mitigating against its high mass, and that tends to say that it will have a lesser escape velocity. So these two competing factors are there. You need to know what the mass of the object is that you're trying to escape from, and you also need to know its radius is, and from those two things you can figure out how fast you have to launch something that you want to be able to escape. So let's think about something that has the same mass as the Earth does, and try to figure out how big would that object have to be in order for its escape velocity to be equal to the speed of light. So if the Earth were to be made into one of Mitchell's dark stars, how small would the Earth have to be? People worked it out. It turned out the Earth would have to be, it's the same mass as it is now, but it would have to be compressed to be the size of an M&M, about 9 millimeters in diameter, in order for it to be so small that its escape velocity would be equal to the speed of light. So people kind of shelved the idea of dark stars. They decided, all right, maybe it's a theoretical curiosity, but we don't really understand matter very well. We don't understand the substructure of matter well enough to think about, could the Earth ever be compressed to the size of an M&M, and if so, what would happen? So 100 years passed by after John Mitchell, more than 100 years, and eventually Einstein came up with general relativity, and he wrote down this equation, Einstein's equation, that I told you about, that if you tell Einstein's equation what matter is in the room, Einstein's equation will tell you how the space-time of the room is curved and how objects will have to move in response to that curvature. Now, I wrote Einstein's equation down in a kind of a simple form that just said gravity is equal to geometry, or curvature is equal to matter. You know, the two are equivalent concepts, and one causes the other. But actually, if I would have expanded the two sides of that equation, they would be really, really complicated. So complicated, in fact, that Einstein thought no one would be able to solve it. He thought it was just an idea. You know, it says something, but it's too impractical ever to be able to solve. So he was completely taken by surprise when another scientist named Karl Schwarzschild, actually while he was in the trenches of World War I, he managed to solve Einstein's equation. So what was the situation for which Schwarzschild solved it? Actually, it was exactly the situation of a black hole, because just for convenience, Schwarzschild said, all right, I don't want to worry about the fact that some piece of mass has a size to it, because then I'll have to worry, what is it like if you're outside the radius of that mass, or what if I tunneled into the Earth? Those will be two different situations. So just for convenience, let me imagine that all the mass of some object was just at one point, and let me put that situation into Einstein's equation and see what kind of curvature of space-time would result. So he did that, and he got, this would be exactly a black hole, so he got a black hole solution to Einstein's equation, meaning that he now was able to say, if all the matter in some object were as small as an M&M and even smaller, if it were all just compressed to a pinpoint, how would space be curved in response? And actually, at this time, people began taking it more seriously as an actual astrophysical possibility, because by that point, people also had learned a lot more about matter. They knew about atoms, and they were at the point that they could realize that it really could happen. If something had a strong enough gravity, it really could collapse to the size of an M&M. There are outward pressures that ordinarily hold an object from collapsing. So the atoms in your body, they have outward pressures that keep them apart and keep them from collapsing. But if gravity were strong enough, if something were really, really massive and the circumstances were right, it could be condensed just to a point. This is an actual possibility, and people took it more seriously, and they began to want to know, all right, so we have this solution now to Einstein's equation. How is the space-time curved by the presence of a black hole, some matter that's been compressed just to a pinpoint? So if you stay away from the center of the black hole, Schwarzschild's solution was beautiful. And it told you all kinds of fascinating things, like that as you would go closer to the center of the black hole, you would see time begin to slow down. You would see intense tidal effects begin to take over. You would be stretched out as long and thin as spaghetti. And all of these interesting and exotic types of things were described by this solution. But if you went all the way to the center of the black hole, all the way to that point where the matter had been compressed, the theory of relativity blew up. It told you at that point the curvature of space was infinite. And this is clearly a problem. If you would make a computer model to try to compute what was happening there, the computer would go up in smoke when it encountered this infinity. And really what's happened is general relativity is only able to deal with the space that's not at the center of the black hole. It can talk about it as long as you stay away from that point, but that point where the matter of some star has been collapsed to a single pinpoint, that point it can't deal with. So here's where we realize that as beautiful as relativity is, and I think it's the most beautiful theory in all of science, it actually is incomplete, which is okay. I mean, Newton's theory is also incomplete, but that's how science works. We never throw the theory out. We say, all right, it has its limitations and it's good enough in certain circumstances, but it has to be, when you want to know to more detail, you have to allow it to be superseded by relativity. Now, general relativity also, we know for sure, is not complete. It also has to be superseded by something else that will be able to tell us about the center of a black hole without blowing up. That's what we would like to do. So here's what we think about. We think, where else in physics have we seen a situation where a theory blew up? Where else have we encountered an infinity like that, where the theory just said, oh, it's infinite, I can't tell you any more about that point than that, and stop giving sensible information? And how did we fix it in that situation? Well, back in the 19th century, there was something called the ultraviolet catastrophe that happened. And that also was a blow-up, and it was a blow-up relating to things happening at a microscopic subatomic scale, and people were able to fix it. By the way, it turns out ultraviolet catastrophe is a very popular name for bands to make albums of that name. So I found lots of album covers called Ultraviolet Catastrophe. That's one of them by a band named Trotsky Ice Pick. So now this is going to be a subplot about the ultraviolet catastrophe. And we're going to use it as a model for how we might be able to fix the situation with general relativity, how it blows up at the center of a black hole. We will use this as our template. So first of all, how did the ultraviolet catastrophe happen, and what was it? It started with this question: what happens to something as you heat it up and it begins to emit light? So for example, a chunk of iron you might have in a blacksmith forge, as you heat that iron up, it begins to glow. First it would glow red, and then yellow. It would get hotter and glow white, and it might even begin glowing a sort of a blue color as it got very, very hot. So people were asking how that process happened, and what was it that made the thing begin giving off light. Newton, so he comes back into the story again here. He had a very good answer that actually was the right answer. And it was that as that object is heated up, we know what heat is. We know that it's the motion of molecules. And as the molecules were moving faster and faster, that would translate to more and more heat. And so Newton said, all right, when those atoms are vibrating, because that's really what the heat is, maybe that makes them emit light. And this was a true answer. People took it and they began analyzing what kind of vibrations would be set up in this chunk of hot iron, that poker that was heated up in a blacksmith's forge. And how would those translate into light that was radiated by the poker as it began to heat up? So here's where they ran into trouble. It was in the 19th century, people thought that the energy carried by any kind of vibration inside the iron of the poker, they thought the energy of that vibration would depend only on the temperature of the poker. And they also thought that any vibration pattern that was possible would be equally likely as any other. This got them into big trouble because here's how the vibrations inside an object would have to fit into that object's shape. Let's say those pink chunks there are representing our piece of iron, and those wave patterns that I've drawn are sort of a schematic diagram trying to show what kinds of vibration patterns would be able to fit inside that object. The way it works is you have to have one complete cycle of vibration, and a crest of a wave, and then a trough, and then coming back again to the neutral position. You have to have an even number, or a whole number really, of those vibrations in order for that to be a viable vibration pattern inside your chunk of hot iron. So here's what happened. The higher frequency vibrations you have, so the ones that have the highest numbers of wave oscillations in a given space, you can fit many, many more of those inside this hot chunk of iron. So the one on the left hand is a low frequency vibration, and only those three possibilities are allowed by the geometry of that chunk of iron. But the one on the right, you can see there are 5 or 6 maybe more actually, lots of possibilities of vibration patterns there. And this is what gets us into trouble if those vibration patterns, the low frequency ones and the high frequency ones, are equally likely. If they all carry the same energy that only depends on the temperature of the object, and if you can fit more and more and more high frequency vibrations inside that chunk of iron, you're going to have a problem. That iron is going to radiate an infinite amount of energy as it heats up, because it can be vibrating at all these different frequencies, and all of them are contributing the same amount of energy, and there are more and more and more of them, of these smaller and smaller frequencies. And obviously the poker is not emitting an infinite amount of energy. Obviously it's actually a finite amount of energy. So here it is. Here is a blow-up, a theory that otherwise seemed to be working well, this idea about vibrations and how they would allow the atoms to emit light. All of that was okay, but it's led to a blow-up. So here's how people solved that blow-up, the ultraviolet catastrophe. What they realized is that it's not really going to be as easy to vibrate at a high frequency as at a low frequency. In fact, those high frequency vibrations, the ones where the vibration was happening, many, many, many crests of the wave were happening in a short space, it turns out those do not have the same energy as the low frequency ones. They actually are more energetic. They're energetically costly. And in order to excite that piece of iron to vibrate at one of those high frequencies, you would have to give it a very high threshold of energy. It also turns out that energy has denominations. It has denominations like currency, so energy comes in small bundles like coins. And it's sort of like how if you came to a parking meter and you tried to put pennies in the parking meter, no matter how many you put in, it won't give you any time. You have to put it in a quarter, and then it will give you time. And it's the same way with trying to get that hot poker to vibrate in a high-frequency fashion. It has to have a lot of energy. You have to put in an energy coin of a very high value to excite it to those high-frequency vibrations. So this fixes the ultraviolet catastrophe, because what it means is what people thought about the likelihood of those vibrations to occur was wrong. People thought that all of those vibrations were equally likely, but no, since those high-frequency vibrations are energetically costly, that hot poker will be much more likely to be vibrating in a low-frequency fashion. Maybe once in a while there might be high-frequency vibrations, but just the way, people aren't spending infinite amounts of money because they aren't buying infinitely many costly products, that hot iron is saving itself from radiating an infinite amount of energy, because the higher the frequency of the vibration, the more energetically costly that is, the higher value energy coin you would have to give that iron in order for it to vibrate in that way. So the hotter and the hotter you'd have to heat it up, the more and the more energy you'd have to pour into it in some fashion. And so those are unlikely. And the iron will not radiate an infinite amount of energy. It's saved from doing so by the fact that energy is broken into coins, denominations like coins. So the catastrophe, the ultraviolet catastrophe, even though physics was like a Cassandra and thought everything was over and nothing was making sense, this solution of instituting these little denominations of energy, this saved us. So this is now a new phase of physics. People realized at this point that lots of different physical quantities, the very important quantities that we can observe, are broken into small denominations. They come in discrete bundles. And the word in physics for these kind of bundles, these sort of coins that are the currency of energy or of some other important quantities like charge, they're called quanta. The singular is quantum and the plural is quanta. And we don't really in our everyday lives experience that the physically important quantities of the universe, like energy, we don't see that it's broken into these little bundles like coins. We think that energy just, it doesn't, we don't see like a kind of a graininess or a discreteness to these coins because the coins are so small. Kind of like how we don't notice the price difference between something that, only a couple of pennies of difference in price. We don't really feel that as a difference. But if the prices of something were very low, you might actually notice small differences in their price. The price of gas per gallon, it might make more difference to you if it's a couple of pennies different at lower prices than at higher prices. So the smaller the price, the more attention you might pay to small differences, and it's exactly the same in physics. If you are looking at something very small, something microscopic, smaller than an atom, you have to pay attention to the fact that actually energy is in these little coins. They may be very small coins and very fine small adjustments, but they are actually bundles. They're discrete bundles of energy, and you would have to take this into account in order to describe physics correctly, or otherwise you'll get an ultraviolet catastrophe or some other catastrophe. So how important really are these coins, this sort of broken down quantum way of talking about phenomena? How important are they to physics? And it turns out they're very, very important. Actually, you need to use the mechanics of these quanta in order to say why it is that atoms are able to exist, why they don't just collapse altogether. So here's how this works. Atoms, in the old-fashioned view, the way we always used to think about them, was kind of like miniature solar systems. We thought there's a nucleus at the middle, just the way the sun is at the middle of the solar system. The nucleus has a positive charge, and electrons are orbiting around this positively charged nucleus. They're attracted to it because they have a negative charge, and like charges attract, and it's exactly like a mini version of planets orbiting around the sun. Turns out this is actually not the right way to be looking at it, and you can sort of see this because it leads to some very strange questions and paradoxes. One of them is, if those electrons, those negatively charged electrons, are so attracted to this positive nucleus, why don't they just go all the way to it? Why are they keeping their distance like that? You might ask the same question, by the way, about the solar system. You might say, if the planets are so attracted to the sun and they feel this pull of gravity, why don't they fall right into it? Well, it turns out Newton already had the answer for that in this idea of Newton's cannon, which was that if something starts out with some energy of motion, it could, instead of falling all the way to the ground, it could go into orbit. Turns out when the solar system was formed, it was formed from a sort of a pancake of dust that had a spinning motion of its own. This spinning motion was inherited by the planets, and they had this energy of motion that gave them the ability to go in orbits around the sun instead of falling into the sun. And that's what's keeping the solar system from collapsing. But we had to go back to the formation of the solar system in order to get that idea. We don't think that every single little atom formed from a cloud of dust and had some kind of, hereditary energy of motion that was keeping it from collapsing. So that explanation is not going to work in that case. We need something else, something that can explain how is it that the atoms aren't falling apart. And actually, to see this, we need one more way in which the microscopic universe not only does it deal in coins, but it also is a game of chance. It's very like a slot machine in this way. So this is how that works. Not only is it the case that if you look microscopically, you have to pay attention to the fact that things like energy are broken into these little bundles that you can only spend, as you would currency. You can't spend a fraction of a penny. Not only that, but also there's another unfamiliar feature of physics when you look subatomically, and that is that if you're thinking about something very small, an electron, let's say, or a photon, something smaller than the size of an atom, you also can't be exactly sure where that thing is. It's a game of chance. If you ask me, where is that electron, the best I can do is I could give you kind of some odds. I could say, all right, in those pictures on the right-hand side there, the orange spots are kind of hot spots where the electron is likely to be. And the darker places are areas where it's less likely to be, but I can't tell you for sure where it is. All I could do is calculate the odds and tell you, well, here are some kind of likely options where that electron might be. So why does this help? Why does this explain why an electron is not just falling into the nucleus of an atom? It turns out that because we can't know everything about that electron, because there always is some degree of uncertainty, and you can't know its position and you can't know its momentum too precisely at the same time, That's what's stopping it from falling into the nucleus. This feature, this uncertainty, is giving it wiggle room. Because if the electron had fallen right onto the nucleus of the atom, you would know exactly where it is. It's exactly with the nucleus. And the fact that it isn't really at any one given place, all the best you can do is say it has, some odds of being one place or another. That's keeping that atom apart. Quantum mechanics is keeping atoms stable. So it's incredibly important to the world. It's keeping the world going, actually. The electrons have been saved from falling into the center by what's called the uncertainty principle, the thing that stops us from knowing the position of the atom, the position of the electron at the same time as we know exactly how it's moving. So here is where we get our inspiration for maybe fixing this blow-up with black holes. We decide, what is a black hole? It's some kind of piece of matter, something like the size of a planet or the size of a star, which somehow has been compressed down and compressed to the size of an M&M and even smaller, to the size of a single point. And as you go close to that single point, general relativity begins going bad and blowing up. Well, this is interesting. Here we have a situation where we're dealing with the very small. We're dealing with a piece of matter that's been compressed to a point. Maybe we can solve it in the same way we solved the ultraviolet catastrophe. That was a blow-up, and it was solved by realizing that we had to pay attention to how things behave at a subatomic level. And we had to realize that the important quantities of physics are divided into these coins, these kind of discrete coins. And not only that, not only are the important quantities of physics divided into these little discrete bundles, but also there's uncertainty. We can't pin something down exactly. We can't know exactly where the electron is. It becomes the case that I can only tell you the odds of where you might find that electron. This is what we think is going to save general relativity. We think that we have to take a look at the important quantities there, and we have to realize that those are divided into quanta. They're described by some kind of quantum mechanics. So let's take a look at how we would do that. Go back to the ideas of relativity. We had Einstein's equation, right? And the way it worked was you told Einstein's equation what's in this room. You told it that the chairs are there and the people are here, and Einstein's equation would do some things, do some calculations, and it tells you, all right, if you walk around this room with a measuring tape and you try to measure objects, I can tell you how that measuring tape will behave and how it will be warped and distorted by the fact that space is curved from those objects that are there. So that means the important quantity in the theory of relativity is this measuring tape, is the way it behaves, the way you measure lengths, the way you measure areas, and the way you measure volumes. And when you quantize a theory, when you realize that the important quantities of that theory are broken into little coins like currency, what you do is you realize, all right, those were discrete. Those important quantities were broken in small bundles. What we think is, this is how space and time are at a microscopic level. They're no longer these smooth kind of things that we pictured. As we think about geometry, we think of a smooth plane or a line that was continuous like this. What we think is that if you would zoom in in a very, very tiny scale of space, you would see that it was somehow grainy. Also, what's the other thing of quantum theory is that you can't know things with certainty. Is the other feature of these subatomic microscopic theories. It becomes the case that you can only give odds of where you would find some of these important things, like electrons. So, what we think is, we will be able to be saved from that singularity, that point at the center of a black hole where general relativity breaks down and tells us that curvature is infinite and refuses to give us any sensible answers anymore. We think that we will be saved by these modifications to our concept of space and time. This is still at a very early stage, but people are now coming up with ideas for a different kind of geometry. If you would zoom in very much, so at the bottom of that left-hand picture, you can see that the representation of space looks very much like a grid, very familiar, very much like a smooth Euclidean kind of geometry that you were familiar with. If you would zoom in and with a magnifying glass more and more and more, we think that the very microscopic structure of space is that it's a kind of foam. So it's broken into pieces like bubbles. And also those pieces cannot be exactly pinned down. It's almost as though there is a foam that's boiling. Pieces can come off, a little bubble like this. Two pieces can reach up and join together into a kind of handle, and that could disperse. So you can't know exactly the structure of space. It has this boiling kind of property to it that's keeping it from being exactly pinned down. And also, it's grainy. What we think is these features are what general relativity needs to incorporate and realize. We need to make a quantum version of general relativity, and that will be the answer that solves that blow-up. And it will say, no, it's not really the case that the curvature of space-time is infinite at the center of a black hole. Actually, you have to replace your notions of space-time with this kind of foam. People are working on this idea in many different, somewhat competing approaches, and we don't really have a final answer yet. But what we think is, it might be that if you were to fall into a black hole, you might get closer and closer and closer to the center of the black hole, and as you did so, you would notice that this foam, this boiling nature of space-time would take over, and it might bounce you back from that point where space would have been infinitely curved if you had believed general relativity. We think in many different approaches, in string theory and quantum gravity, these are warring kind of fields, warring areas of physics that are trying to advance beyond general relativity. But the exciting thing is, even though people disagree on how to do it, we agree that there probably is this very different nature of space-time if you just zoom in very, very small. And we think we're about to understand something about geometry and to take some of the beautiful ideas of relativity that tell you that what matter is really doing when gravity results is that it's curving space and changing its geometry. There's going to be much more exciting geometry for it to be changing. There's going to be this boiling and reconnecting and bubbling foam, and that's the goal of physics right now, of this branch of physics, is to understand how this foam works, what it is, and how that's really going to save us from falling down a black hole. Thanks.